Scene 1, 2, 3. Alright. Guess who has two thumbs and showed up 5 minutes late? This guy! Oh, wait, hold on. My model doesn't have thumbs. Guess who has two eyes? I was a little bit late. This guy. This guy's. Sorry about that. I may or may not have just been, going over stuff from last week. I'm barely doing the promotions now. That happens. Alright, so last week I went over kind of how math can apply in real life, and I kind of like this bouncing around between, different types of maths, right? Where, some of it's about, things that you can use to apply to what you may or may not know. Like the importance of math and how to use it in real life. And the other part is to actually do the thing. Now, oh jeez, I only have like I'm way behind. I am way behind. I'm gonna try to not let like a blank screen show up. But I'm kind of pressing all the wrong buttons in the wrong order right now, so that might happen. Okay, gotta get this started. Login, full screen. My board. Session 25. Uh-oh, this is the wrong one. Okay. So there's that. My face is not on. It's frozen. Alright, getting up the lesson plan. Let's just pick a page. Boom, random. What's this? This is already polynomials. Didn't we do that? Did I just pick the same random page? Let me skip backwards a bit. Or maybe I should go forwards. Oh no, 12 seconds. Okay, my face is working. Yay! It worked. Can I cross my eyes? I don't know if that worked. Alright. Sorry, just testing some silly model stuff. So today we're going to go back to what this textbook describes as intermediate algebra. And I think... What's this? You know what? Let's try this thing. That's mapping relations and functions. Oh, I see. Okay, sorry, I'm reading this and I'm not sharing my screen. My apologies. Let me clean up this dead air with some first promo, and then I'll do the thing. Is on functions. Let's see. How do I think I have to go here, and then I go here. Yeah. So I sometimes I always forget out, like, how do I chat? Is on functions. Hey, there it is. All right, looking good. Okay. So today's lesson is going to be on functions. Very cool. Now, I think this is going to be a little too general. But, what is a function? No, I don't want to do that quite as much. I want to do a graph of a function. But I'm trying to find out which is a nice page to copy from, because there's a lot to look at. Okay, you know what, let's just do here. I think I'm dilly-dallying a bit much. So, graph of a function. Functions are basically equations that kind of make a shape in a very simple terms. And it's gonna look a little something. Copy. And, sorry, flickering. Paste. It's gonna look a little something like this. Let me just go off to the side. Oh, that's not what I wanted. Ooh, there's a lot of flickering today. Okay. So, that didn't happen. Sorry, I dropped something. So a function is basically a math equation wherein you have values and they make kind of like a shape, right? Now, it's not normally a shape like this. This is actually the wrong way to do a function. So let me just erase that. Some common ones are this kind of wiggly shape, which could be something like sine or cosine. Kind of like a straight line, which would be like kind of a very simple formula. Maybe something that's a bit complicated is something that is like that. I don't know. It could be all kinds of crazy things, right? Now maybe you might be asking, why is this important? Once again, because that's, I think, the important. Well, I shouldn't repeat myself, because I'm just repeating myself. One of the things to keep in mind in functions is that it's the part of math and algebra which can be very visual, which can really help students who have strong visual learning, right? In this example, you can even look right here, where you just kind of line up the numbers with the values. So you have right here, -3 and 3, -2, -1, 0, and then 1, and 2, and so forth, right? And so this is the kind of special kind of math where maybe before, when it was someone just kind of doing the numbers, maybe in their head, and they just have to memorize the formulas, like, oh yeah, what's a square root of 81? Oh, it's 9, right? You looked at a chart and you memorized it. Or maybe you can kind of, you know, understand how, you know, addition and subtraction works. Easy. But because this is more of a visual medium, I think it kind of can reach out to someone who might think, oh, well, this is something that I'm actually creating with these numbers. Or rather, I have to relate the visual aspect of this thing to a function, right? Like, oh, yeah, it says domain and range there. Okay. Oh, yeah, this is actually nice, right? It is the graph of a function of, I believe, are these absolute values? Yeah, absolute values. An absolute value basically means when it's negative, it becomes positive. When it's negative, it becomes positive. And when it's positive, it becomes positive. That sort of thing. And so, in this way, oh, pardon me. Whatever number that you put as x, right, as your x value, whether it's negative or positive, it will become the same value as y. And so it's not just some kind of esoteric, okay, well, it's just transforming numbers into a random positive value. No, it actually has a physical, visual purpose, which is very neat. And I'm blocking this with my head. I'm so sorry. Whoops. I have to be conscious about that. So, because this is a mathematical formula, or at least a formula and a way in which you do graphing and functions, again, you gotta look at it. It's very cool. And then you get these crazy shapes, right? Now this is, of course, just kind of the introduction to functions and how it looks like on an XY graph. So you just put these shapes into there, right? But then once you have an XYZ graph, then that's where you get kind of crazy, where you don't just have like, you know, maybe a shape, you have like a sheet, or you have these weird, crazy, worm-looking things. Is this? I forgot how to draw these things. Imagine this is 3D. Imagine if it's 3D and it looks cool and it's like, oh wow, it's all this kind of stuff. But that's like way complicated. That's more something else. Just to kind of give functions is basically to give a visual and a corresponding shape to the numbers, which is pretty cool. And you know, this is kind of the beginning of where when people look at bars, charts, and graphs. So say, for example, if someone has a set of numbers, right? It's usually something like months by number, right? Let's go back to business. Let's pretend it's January. Whoops, that's not January, that's Jan. February, March. Good enough. Then you have like 100, 200, 300. And this could be corresponding to anything, right? The month for maybe the amount of people that show up to donate winter clothes at a charity. Sure, why not? And you want to keep track of that, right? They say, okay, so in January we had like 270 people show up and they brought a bunch of clothes, or 270 articles of clothing. In February, no wait, hold on, it'd be the opposite way. It'd be like this. In January you only have like 120. February you might have 150. And then come March you get like 300. 310. And the reason why might be because, you know, everyone's using their winter clothes, even if they're a little tight and worn out during these cold months. But they think, okay, yeah, you know what, it's the end of the winter season. Let's just give them all away. And we'll get new clothes for next winter, because everyone's growing, or this stuff's really worn out. And then all of a sudden you have a huge influx of winter clothes during, like, the spring or start of summer, you know? So that's kind of funny. But again, not to focus on that example too much, but rather that to use numbers, to put them into visuals, and to explain how they correspond to certain things, like January, February, March. Maybe you could even make this into a sort of, not quite an actual function, but like a pseudo function, right? Where maybe you could say something like, you know, as yeah, this song goes. As the how would this work? As the temperature rises. No. I'm trying to think. What would be a formula for if the temperature rises? And then that means that the more winter clothes are donated. But then it's only for like the first month or two, and then after that it stalls out. Yeah, I don't know. Let's pretend as if we know what we're doing, and are able to make up these complicated formulas on the fly. Because again, that's the tricky thing about math. Usually they're just kind of equations and they have you solve it. There isn't really a dedicated thing to making the equations unless they're similar to other things that exist. So for example, if I wanted to make a function that's similar to this function, that's fine. But if I'm making something that's similar to a data set that kind of has like made up numbers and weird gaps, that's a little bit more tricky, I'm not gonna lie. Well, I suppose that's why people use graphs then, right? They don't use graphs and turn them into functions normally. You know what? Let me just skip this example. Because they don't usually use graphs and turn them into formulas. Because let's say, for example, right, you're a business, right? And we'll change the example. Maybe say you guys are selling spring clothes. I don't know why clothes are on the menu for today, but let's just say, right? You're selling spring clothes and then all of a sudden in March, sales goes up. Woo, that's great. And then you could try to break this down into graphs, right? You could even use historical data. This happened in 2025. This happened in 2024. This happened in 2023. You can go on and on and on and say, like, we have all this historical data for like decades and years on end, where this is the same pattern every time, and we're going to make a solid formula function for this equation and say that this is the guaranteed formula for success, right? But then there's always something that can happen, like a what's colloquially known as a black swan event, wherein something totally unexpected happens, right? Like COVID. And so when that happens, all of a sudden, whatever formula you made to say, oh yeah, this is the secret to success, where it makes money, now it's all gone to shreds because of a totally unexpected event. Whereas when it comes to actual functions, right? This works for any number. It is the same. It works every time because these are hard values and hard numbers that we work with and that they do not fail. And so when I'm trying to apply real-world data sets to create functions, which is used to basically create a predictive market, such as things like future sales or someone planning to buy and sell stocks, then they always are going to run into trouble because at some point, you know, reality is going to get in the way, like with COVID, and then all that assuredness is all lost. Whereas with actual functions and math, there isn't that issue. Again, I know a bit of rambling on, but that is to say that, you know, rather than think that these things should become functions, you should use functions to try to apply to your data sets and not the other way around. That way you won't get disappointed. That way you're able to account for other events. Now let's see, how would that look like though? Well, if you know, what is something that is going to happen for sure? 1 equals 1. It's kind of easy, right? One equals 1. Guess you could say $1 equals $1. And you can't really do a currency change because that's subject to change. You can't do assets. I guess like a bond. Bonds. A bond is a certificate. Okay, again, I'm not an accountant, so or financial advisor, but as I understand, a bond is something where you pay into it, let's say $10, and it gets held for 30 years, at, let's say, 4% interest rate. And then those $10 become magically. Let me bust out the calculator for this one. Now, if I recall, it's not, it compounds. So if I recall correctly, it does compound. So what that means is that, instead of just the $10 and the 4% on that $10, and it's just that same number every single time, it's actually the $10 plus that 4%. And then so the first year, right, it's the $10 and the 4%, and then the next year it's the $10 plus that 4%. And then it's the 4% of that. And then the 4% of that. And it just keeps kind of going and going. I guess I should probably do it like this. Actually, the real formula would be like this, right? It would be, what was it? 4, no. I think it'd be like 1 plus 10 plus 1. 1 plus 0.04 times 10. There we go. So that'd be 10 plus, well, let's just leave it like that. Because then what happens is that then this gets nested. If that's x, then it becomes x times 1 plus 0.04. And then if that equals y, then it becomes, the next year, y times 1 plus 1.04. And just to kind of, put it into numbers really quick, in this small example, the power of compound interest is such that your $10 after the first year becomes 10 times 0.04. 10 point, is that right? Just 4? 10.4. All right. And then all of a sudden you have 10.4 times 1 plus 0.04. Yeah. Or, I mean, yeah, it's basically times 1.04. I don't know why I'm overcomplicating it. Because you could just add it. Yeah, it's not like, well, I mean, okay, yes, you might have it separate, but you would just kind of add those two together, the 1 and the 0.04 in the middle. So it's just like times 1.04. Okay. So then for this number, instead of y, you'd have 10.816. And that becomes 11.24. So within the period of about 3 years, all of a sudden, your $10 has magically become, right, $11.24. And over a period of 30 years, let me bust out the real calculator for that. Let's see, $10, interest rate of 4, investment lengths 30 years. Calculate. All right. I think I did this exact number before. 32.3. Or sorry, 32.43. Now 30 years is a very long time. But if you're able to get a bond with that kind of interest rate, the higher the interest rate, the better, right? And so because these always work exactly the same and an only variable is the percentage itself, this is a function. All right. Whew, long way to get back to functions. But this is the most realistic, real way version in which a function can work, in that it is kind of like a not linear function. A linear function just, well, maybe it is. I forget. Because I think linear just means like it's a straight line. But here, it kind of goes up like that. It just kind of goes up and up and up. And the more time you put into it, the more that the interest kind of multiplies upon itself. And it goes higher and higher and higher, right? 4% of $100 or $10 isn't much. But then once you start looking and it goes up to like, $1,000 and 4% of that, then it looks better, and then it just keeps going up and up and up and up and up. Well, not like that. Like that. Now, bonds aren't quite going to get you this crazy high, right? Maybe they'll get a little right there. Right before the real money's made. Unless you put in an insanely high amount. Then you'll start to notice those greater returns. But basically, you could think of like, okay, 30 years at 4%, you basically tripled your money, right? So then if 10 becomes 32, then maybe like 1,000 becomes 1,000, 3,200. Just assuming, right? Because I'm just scooting the zeros, but the formula's still the same. So then 10,000 would be 32,430 something. Okay. And that is a way in which, again, you can apply a function to money in the real world. But that's a way in which the system of finance uses functions for money. You're not putting money or other kind of data sets that correlate into making its own function, because that's how you get into trouble. I really want to reiterate that because that's huge. All right. Now going into functions properly, 30 minutes later. This one's quite nice and easy. When you have absolute values, again, it just flips it to positive, and wherein, whatever number you have, it's always going to look like this. And if you're going to be further down the track to the negatives, it's just going to keep going this way. Positives are just going to keep going that way, basically until infinity. And I believe that's called the domain, where the domain is how far it can spread among the x value. So if you can put in any number for x, and it will just be fine. Negative infinity, positive infinity, doesn't matter. It works with this function, right? Now with the range, though, that is specifically for the y values, and only the y values, just like how the domain's x values. So no matter what number you put, the limit is always going to be 0, and it's just going to go up and up and up either way. Because, if you put like negative 100, it's still going to be like way up here. Positive 100, it's going to be way up here, right? Basically, no number you put can get below 0, because the closest you got is 0 itself. And that's just because of the nature of absolute values. Oh, that was nice and easy. That was quick. Well, let's see what more we can get. Ooh, this has the solution. Okay, all right. So I'm going to try to copy this, but without the solution in it. Wish me luck. Okay. Copy. Paste. All right. Let's get to it. So here we have the graph of the function to find its domain and range. Write the domain and range in interval notation. All right. Well, they always gonna have this beginning part, right? And what we could do to try to kind of figure this out is we could kind of brute force it just a wee bit. Oh wait, what? Oh, we're just talking about the domain and range. Oh, we don't even need to look for the formula. Okay, hey, you know what? This is why reading comprehension is important. So what I was gonna try to do is actually figure out the function itself. But again, one of the most important things you can do in any class is read the instructions very carefully. We're just finding the domain and the range. And you write the domain and range in interval notation. Okay. Easy. You eyeball it. You just look at it. You don't even have to think too hard. You don't have to figure out the function. You don't even have to, you know, count all the numbers in between. You could basically ignore a lot of this noise in a sense because you just want to find out where. Oh, they even have the answers highlighted for you though. Oh man. Okay. Well, that's no fun. But there it is. So the domain. Let's do it like this. Interval notation is just kind of this kind of directions. And ooh, it's a bit different. I'll explain a way in which these are actually important because I think that let me get to that in a second. Actually, what? Let me get to that in a second. Yeah. All right. So for the x values, we have this right here. It kind of looks like -3. To the right, as far as it stretches, it looks like +3. That's cool. To the y, the bottom part looks like -1 because it goes right here. And to the top part, it looks like 3. There, easy. All right. Now, why is interval notation important? This is so easy. So normally you would think, okay, this just seems like a formula and a structure with which to solve this very niche specific math thing, which I will not use. Yes and no. In the way that it is presented with domain and ranges, where you only are graphing a point on the graph, and, sorry, if you're using domain and ranges like this, kind of, right? It kind of goes from one side to the other side. Now, if you're doing the traditional, not domain and range, but just interval notation to figure out points on a graph, right? Where if you're looking at, let's say, this point right here, that one will be known as, and if you read it, the x value is 3. Oh, and they're almost always in an xy coordinate. And the y value is at 1. So this point on the graph is going to be known as 3, 1, right? And as far as a practical, real-world application for this, I got you. Video games. All right, hear me out. This is actually really important for video games. So interval notation is actually used in maps in video games. Say, for example, if you have a big map of this thing, right? And you're in this fantasy world, and you want to get the coordinates of this boss because they don't have like the exact coordinates. You check on the wiki, and they say, oh yeah, the guy's at like negative, 20, +10, right? And the map is kind of like in an XY grid, but they don't show it like that. They just show it as a map, right? So these lines are imaginary. But what you would do is maybe you could kind of look at the map of where you're at, and if it is a centered thing, right? Check on the wiki. It'll have the coordinates, an interval notation of where this thing you're going to be looking for is at, right? And if you have a mod or if they have like built-in coordinates in the game, then when you put your mouse over, maybe in like the little tiny text right up here or somewhere, they'll say like, oh yeah, this is where your mouse is at. So if you put it right here, then it'll be 0, 0. And if you put it somewhere else, you know, negative 20, 0, right? Stuff like that. Follow and figure out, okay, well, if negative 20, 0 is there, but if I put my mouse right here, then no, that's negative 20, negative 10. That one more what about right here? Here. Yeah, this looks like about negative 20, 10. And you're like, aha! Alright, so this is where the boss is at. My character is some kind of little triangle facing this way. So I need to mosey on over this way, and then there I am. I was way off in the map, right? And there you go. Now, again, you could just reference the wiki, and you could just look at the game coordinates, and then you can kind of use that to kind of figure out where this thing is and where you should be going. But that doesn't change the fact that using interval notation, using coordinates, using charts is actually not just important, you know, in real life navigation, but also in video games too. If you're trying to get to specific spots, find specific NPCs or whatnot, treasure, what have you. Um, so yeah, even though you might not, you feel like you might not use this kind of stuff in your real life, and it kind of applies to when you're just trying to have fun and then not waste time running around, getting lost. Unless you enjoy that kind of thing. If you don't like looking up the where things are and you just want to kind of explore, that is completely fine too. But what I'm saying is that these systems exist to help those players who do not want that, or people who just get lost, or you know, people can just kind of help each other. Yeah. So interval notation, surprisingly necessary. And again, I think a video game is a common example because that's kind of what this platform Twitch is mostly known for. But it's also can be used in like, well, navigation. Not really. Okay, I say not really because normally if you look at a map, right, you there's not going to be like a point where, let's say, you got this road, you got this road, you got this road, and you got all these side streets, and you want to get to here, right? Um, sorry, you might want to get to here, but you are located here. Well, then maybe you're not going to actually use interval notation for that because, you know, unlike video games where you can just like hop over things and crash through people's houses, you're going to actually have to follow the rules of the road and go to where the streets are, not to where the destination is. So for actual map reading, just, you know, to kind of shake off a bad habit, if you're used to reading maps in video games, that's not the same as reading a map in real life. Because reading a map in real life is knowing, okay, what is the name of this road? How far do I have to go? What is the cross street? And which way do I head? Facing this way, you'd probably be heading left, but cardinal direction east. And then here's another cross street, which might be an on-ramp to a major highway. And then you're going to head that direction north, and you're just going to ride that out for a certain number of miles. And so when it comes to actual map reading and trying to navigate through a city, either through transportation, subways, walking through like a park, cardinal directions will help you more than something like interval notation. But for video games, where things are fixated on a point on the map, yeah, they're fantastic. Yeah. Okay, all right. Sorry, I got a little distracted. It's just I haven't touched these math concepts before, and it's kind of fun to see like, well, what's the point? Well, there's the point. So you can play games better. So you can invest. Uh, okay. All right. So here's a few more that I could do the. Let's just do one. Well, domain and range. Again, it's just like kind of looking at. Sorry, I'm looking back at the textbook. But you just eyeball it. That's kind of the tricky thing, right? So when trying to explain these concepts to a student who cannot or is struggling to understand, they're better able to explain what is the issue, right? Typically, it's why do I need to know this? But sometimes it's more like, well, what do you mean just eyeball it, right? Maybe it might be, um, what if we're not covering this, or what if we already covered that, or what if this thing that we're covering is built on something else that I don't understand? So, I would say for any student that is struggling with this subject of domain and ranges, you're just probably gonna have to memorize that domain is for x, range is y. And you just gotta look at the highest point and the lowest point, and then the furthest points from the left and right. And you should always kind of make like a box like that. So here's another one, right? In fact, let me get a few more. Yeah, there we go. Oh, hey, there it is. So looking at this, right? You can just draw lines. Like if it's too hard for you to just kind of, count up and down like that, just draw a big long line. Like first you look at the x and x, right? So you just draw a line there, draw a line there. So you're looking at the left and right sides, which are the furthest there. And then from the top and bottom, you look at those sides. So this is the topmost point, this is the bottommost point, right? And these shapes, they'll always basically make a box. This is kind of a brute force way to do it. But, doing it again, leftmost point, rightmost point, bottommost point, topmost point, right? And wherever these things touch, that's gonna be your number. So then for here, the domain would be, let's see, x is all the way over here, so counting down, -5, because this is the line here. So this line's -5, and here this line's 1. Cool. Oh yeah. But then for y, it's a little bit different. The range. I erased that thing. And the range is not the same because they're not the exact same numbers. They kind of look, they're in the similar place, but it's actually -4 and 2. Because you got to count from here. Yeah, and again, I can go over and say the same thing and just repeat the numbers and solve this equation. But the point is that when you're looking at it, try to eyeball it. If you can't eyeball it, then you could draw lines on it. If you can't draw lines on it, oof. Why can't you draw lines on it? Maybe you could just bust out a piece of paper, right? A sticky note, a ruler, something like that, and just be like, yeah, that kind of looks like it. Get an eraser or a pencil and just like block it off, and you're like, all right, that makes sense. Uh, let's see, eraser here, sticky note here, pencil right here, right? And then your finger right there. And that's how you figure this thing out. As far as a box shape, you just count the numbers. Again, this is kind of like a silly way to really kind of shortcut it. But again, these concepts should not be like crazy, mind-numbingly hard. Let's see, what else? How else would someone struggle with this? I imagine maybe if they don't quite get the concept of x's and y's. Um, the way that x's and y's relate to us is because, you know, we live in a 3D space. So any time you move something in an actual real world space, like let's say here's a cube, right? Even then, right? Cubes are kind of abstract. And I drew that poorly. That doesn't help. Boom, boom, boom. I think that's cubish. It's not perfect cube, but it's cubish, right? And then a real example of a cube that you might encounter is something like let's say dice, right? Four, five, a pair of loaded dice. 4, 5, 6 dice. All right. Now, when looking at this object, this box-like thing, right? If you're looking at just the face, right? Ignoring all these other parts, just looking at one side of it. This one side, long ways is x, up ways and down ways is y. Right? So if you're looking at how many, you know, how many dots, how many points are in this XYZ graph of the 6 side of the die, then you have here and here. And because it's all in up, basically you only have 2, right? 1, 2. And even this is still 1 and 2, 1 and 2, because they all line up on the same point of the X line, right? And then for the Y, you have 3 points each, because they all line up along the same line on the y-axis. Even though there's 6, as far as the y can see, right, there's only 3, because this one behind is being blocked by this one, if you think of it that way. And these lower ones are blocking these upper ones for the x-axis. And then when you get into something like z-graphs, that's where you kind of look at the whole shape itself. And that's where something becomes 3D, wherein it is not just the x and the y, but the whole thing itself. So, say for example, you're not just looking at the points on the dice, you also want to look at the volume. Or is it mass? I forget. There's a very specific terms between volume and mass, but generally, how much stuff is in this dice, right? And so, I think volume's like size, mass is like weight. Anyways, so if this is going to be one side, let's do funky numbers. Let's do 1.2, right? That's the length right here. The height is 1.2, and then because it's a perfect cube, the width will also be 1.2. That's going to be the z. length, height. All right. So what is the surface area if this thing is like 1.2 inches all the way around? Well, no, surface area is something different. What's the area of one side? How about that? Yeah, yeah, yeah. That'd be 1.2 squared, which is 1.44. And that is this whole area, right? And what is the volume for the entire dice? Or, well, you just do that number times 1.2. And so this whole thing, 1.728. Now, this is not the kind of math that, because, again, I'm using the point values, you might have a calculator. But that is kind of a different way in which to explain concepts of x, y, and z, not just in an abstract math way where these graphs that don't have any relation to the real world, but in a way in which it is a physical object on a 3D surface that might be common that you can use to think of, okay, what's the size of this thing, right? Now, why would you need to do that? I don't know. Maybe you want to check if the dies are like, oblong or weighed wrong. And, you can use like little measuring tools to figure out, okay, is someone cheating using these things? Then maybe there's something off with either the weight or the size or stuff like that. I'm not sure. But, oh, shoot, only 4 minutes left. Okay, let's see what else. Let's see what else I can do. Oh, it has the answers. Okay. Mm. All right. Going back to here. Uh, let's post. So again, the thing is that the textbook I'm using is not like an official, specific, school grade textbook in the sense that, a lot of those things um, change by additions, and they can be like tailored and they're rewritten and all this kinds of stuff. This is kind of an older one, and I believe it is the teacher edition, the master edition. I forget what it's called, but it's the one that has a lot of the stuff in it, where it also like gives the answers pretty easily. Why? I guess it's so that they could solve it faster. But again, it makes things a little weird because it's like, okay, well here is the equation, right? That we're using as an example. Well, I think are there just like plain ones without? Yeah, no, it's just a lot of this stuff kind of just has the answers in it. Anyways, it only kind of explains the concepts, but it kind of shows you the answers to these concepts as well as they explain them. There isn't really kind of random examples to work with. And even if there was, I probably wouldn't use them. Because this makes it challenging in a weird way. In that I get to challenge myself to try to not look at it, and then once I do look at it, then I get to figure out if I'm right or wrong, like within seconds. So, there we go. Use the graph of the function to find the indicated values. So it looks like they're not actually giving us an actual equation to plug in numbers. Because think of it this way, right? This could have been an equation. This homework assignment could have had this graph, as a very specific equation that you would have had to plug in the numbers for every single time. And then maybe you might get like, it would have been complex looking. But instead, they kind of give you the gimme and say, okay, well, just eyeballing this, you know, where on the x-axis, what's the values? So that's nice. So for here, right, if x equals 0, which would be right about here, what is the other value? Y. Well, it's probably 0. Now let me just double check. Yeah. Yeah, it's right there at the bottom, right? When x equals 0, the function across the y-axis is at 0. So f0 equals 0. Okay. Alright, so they want to write it like as if it's the y equation. Alright, now I kind of get an idea. Alright, equals 0. Alright, now when f equals 3 over 2 pi. Right here. Oh, they even give you the answer. Equals -1. Ah, they even write it right here and they highlight it. Ah, that's lame. All right, you know what? Let's make up our own, right? Here, I'm gonna go like this. Wee wee. All right. And it looks like every time it touches the x-axis, it becomes something. So this is gonna be 3 pi. This one's gonna be if the line's like that. This one's gonna be 4 pi, 5 pi, 6 pi. Alright, good enough. Alright, what's this one? Alright, so this might look crazy. But the thing is that functions are insanely consistent, right? So if I were to say, okay, well, what's this part right here? It's probably... well, if this is like 1, 3... Let's see, 1, 2, 3. So it looks like they're counting by half pies, right? Here's 1 half, here's 2 halves, which is 1, 3 halves, 4 halves, which is 2, 5, 6, 7, 8, 9. You got 9 over 2 right here. Pi. Cool. And that'll be our function. Alright. What's the answer? Well, the thing is that because this thing is a very consistent formula, it's all the same all the way around, and it doesn't quite touch it because I draw poorly. But it's still going to be just the same as it is over here and the same it is over here, in that the answer is just going to be 1. So again, that's a nice thing about functions and stuff like this, is that you can just kind of add on to it, make up whatever number, but it'll still work out. Now you still have to use the pattern in which they're applying this though, with the, you know, pies, but I think it checks out. Now, unlike the other ones, I can't look up the answer, but I'm like pretty sure I'm right. Because you can also do like patterns, right? Let's see. 3, 4, 5, 6, 7, 8, 9. How will this pattern be? Every pi that comes after an odd number, the half step is negative. So 1, -1, 3. Sorry, I'm explaining things that is a little bit beyond what I'm trying to cover here. Point is that functions, you just kind of eyeball it. But that's if you have the graph. And again, it's nice and great because graphing functions is, again, a way to visualize the math homework rather than just have it abstract. And you can even have fun brute forcing it if you're allowed to. At least for this level with this kind of stuff. And the reason why these things are important is because with functions, you're able to use those to apply as a direct formula to understand the compound interest of bonds, but not by using data sheets to make a formula for something that you expect to happen in a business later on, because then that's just not accounting for totally crazy events that no one expects, like COVID. And things like, understanding interval notation, which is used here in math homework to find domains and ranges and stuff like that, or points on a graph. Interval notation is also very important for understanding reading video game maps, right? Not real life maps where you have to understand, freeways, cross sections, and off ramps. But video game maps wherein maybe you might have a wiki and look up the coordinate of an NPC or location, and you can kind of use that because these things are actually secretly XY graphs. It's pretty cool stuff. All right, and that's it for today. I think next time I'll be going over more money math. Yeah. Whew. Boy, what a session. And again, if anyone needs help with tutoring, just feel free to say so. I think I have a student lined up in 2 weeks, so quite a ways, but I'm looking forward to it. Until then, I hope everyone else who came by, thank you again for coming by, checking this out, and I hope you all have a good night.